Welcome to this webinar. Before we begin the presentation, I want to provide you with a few housekeeping items. On your screen, you will see a taskbar with icons. Each icon is assigned to a particular element of today's webinar. Click on the person icon to learn more about today's speakers. Throughout the presentation, you can network with others or submit questions to the speakers in the Q&A and chat box next to the slides. Download resources from the cloud icon. After the webinar is over, please take our survey to tell us how we did. Today's event is being recorded and archived and will be available within 24 hours. For on-demand questions or comments, send us an email by clicking Need Help? Email us. If you experience any technical issues today, please refresh your browser by hitting F5 for PC or Command R for Mac. And now I'm excited to turn it over to today's moderator.
Good afternoon and welcome to this webinar, Getting Started with VRF. This event, brought to you by Engineered Systems, is sponsored by Mitsubishi Electric Trane HVAC US. I'm your moderator, Herb Warple, Editor-in-Chief of Engineered Systems. Thanks for joining us. Today's presenters are Kevin Miskowitz and Victor Chale. Kevin leads the development and execution of commercial product strategies for Mitsubishi Electric Trane HVAC US. Most recently, Kevin served as the Director of Commercial Marketing, leading the marketing strategies, programs, and initiatives for the division's commercial product line. He is a certified Lead Green Associate. Before joining Mitsubishi Electric in 2014, he was the Product Manager for Condensing Units and Controls at Heatcraft Worldwide Refrigeration in Stone Mountain, Georgia, and he previously has held global marketing and product management roles in the Consumables Division at NCR Corporation in Atlanta. Kevin earned a bachelor's degree in business administration from the University of Dayton. Victor Chale has been with Mitsubishi Electric Trane HVAC US for 4 years and serves as an area sales manager, working with developers, architects, consulting engineers, and contractors on commercial properties. With more than 25 years of experience in the HVAC industry, Victor's held a number of sales, marketing, and management-related positions for HVAC design-build projects. An engineer by training, Victor earned a bachelor's degree in industrial engineering from Purdue University. Don't forget to submit your questions, and later in the program, Kevin and Victor will address as many as possible. Today's event is being recorded and will be archived at www.esmagazine.com/webinars. And now I'm excited to turn it over to today's first presenter, Mr. Kevin Miskowitz. Kevin?
Thank you, Herb. Good afternoon to those joining us on the phone, and welcome to the Getting Started with VRF webinar. Vic and I are excited to spend the next hour discussing the HVAC industry, and more specifically, an introduction to Variable Refrigerant Flow, or VRF, along with sharing a few real-world examples of successful applications. Today's webinar will cover the following topics: identify VRF system components, as well as basic best practices for application and installation, explain the similarities and differences between VRF systems and traditional HVAC systems, dispel common myths and misconceptions about VRF systems, and at the end, we'll share a few real-world examples of successful application. We'll be sure to leave plenty of time for questions at the end of the presentation, and we look forward to answering them for you today. Be sure to submit them throughout the presentation by using the Q&A function within the presentation software. First, let's start out with an overview of variable refrigerant flow technology. Instead of moving conditioned air through ductwork to the space requiring conditioning, VRF delivers conditioned refrigerant directly to that space, eliminating the requirement for long runs of ductwork. This eliminates those inefficiencies that come with moving conditioned air a long distance through ducts and provides a more energy efficient, quiet, and flexible way to condition a space. In addition, VRF provides the ultimate personalized comfort experience for a building's occupants. Each space or zone requiring conditioning will have their own network of indoor units. This network of indoor units is controlled from within the space, providing the occupant with the ability to personalize their comfort. Some systems can even cool some areas of a building while heating others from the exact same system. This leads to happier tenants and fewer comfort control complaints for building owners and facility managers. Finally, due to the design flexibility of VRF, it can be applied to a variety of building types and applications. from adding capacity to an already taxed HVAC system on a college campus, to providing K-12 schools with a quiet, efficient way to cool classrooms, to conditioning a new high-rise construction project, VRF is the optimal HVAC choice. VRF technology has been in use around the world for over 3 decades and is the prominent and oftentimes default HVAC technology of choice. Its worldwide popularity is largely driven by factors such as the high cost of energy, tight construction requirements, and limited space for mechanical equipment within a building. As you can see, VRF systems make up 80% or more of the HVAC systems applied in locations such as Europe, China, and Japan. In 2003, VRF technology was introduced into the United States market and has experienced rapid growth ever since. We firmly believe VRF is the future of heating and cooling technology, and that the technological advancements will continue to come in the years ahead. At its most basic, a VRF system consists of an outdoor unit connected to a network of indoor units through refrigerant piping, as we discussed a minute ago. The system's operation is governed by a network of controls, which read data from a variety of sensors located throughout the system. VRF systems can be applied in 2 basic configurations: air source and water source. Air source systems use air as the heat transfer medium, expelling rejected heat into the air outside of a building. Water source systems, on the other hand, use water as the heat transfer medium, expelling rejected heat into a water source typically located inside of the building. Both configurations, air and water, maximize energy efficiency for the building owner. The outdoor unit contains the compressor, condenser coil, heat exchanger, fans, and electronic controls. Outdoor units may be used on their own as a single module or twinned to increase capacity to achieve the building's conditioning requirements. The indoor units contain a fan, filtering mechanism, heat exchanger, and controls. The indoor units come in multiple styles, which increases the application flexibility of the technology. Indoor units can either be ductless, which means the requirement for ductwork is eliminated, or ducted, which incorporates short-run ductwork from the unit into the space requiring conditioning. Indoor unit styles, as you can see on the screen, include horizontal ducted, vertical air handlers, wall-mounted ductless, ceiling cassettes, and more, up to 11 or 12 different styles depending on the manufacturer. Now that we have a very basic understanding of VRF systems, their operation, how the indoor units, outdoor units work together, and the basic components contained within each, I'll turn the presentation over to Vic Chale, Commercial Area Manager for METUS, for deeper insights into the world of VRF technology, including talking about some of those myths and facts of the technology itself. Vic?
Thanks, Kevin. My name is Vic Chale, and I'm a Commercial Area Manager here in Chicago. I've been with Mitsubishi for just about 5 years, but prior to that, well, actually, as I was coming on board, I'm reminded of a story that sort of ties into this first myth, which we've got sprinkled throughout the webinar. I would tell my friends, hey, I'm starting a new job, and I'm going over to Mitsubishi. The first response was, so are you selling cars? And I would reply, no, I'm not selling cars. And then the second question was, well, are you selling TVs? And I would assure them that I wasn't selling TVs. And the last one was, oh, so you're going to sell those wall-mounted units that we see all over the place? And I said, yes, I am going to be selling those. But one of the things that you should know is that even though the wall-mounted unit is ubiquitous, you see it everywhere, and is the most popular indoor unit in internationally as well as the U.S., we have 5 or 6 different models of indoor units. So that is the myth that all indoor units are wall-mounted. I'd like to start off by introducing the most basic VRF system, and it's the heat pump system. The way most people think about this, or rather the easiest way to sort of explain it to people, is to say, let's take a look at your house. You've got a condensing unit outdoors, and that's sort of like our outdoor unit. And then on the inside of your home, you have a furnace. So imagine taking that furnace, shrinking it up, and then putting multiple furnaces throughout your house. In fact, put one in every room. That's in essence a VRF heat pump system. So let's take a look. So we've got a condensing unit here on the outside. Using refrigerant piping, we're going to pipe that up to 50 indoor units of various styles. Now, in a heat pump system, the system will be in all cooling or in all heating. Each indoor unit then can modulate how much heating or cooling it's providing to the space. But in fact, the system will be in heating or in cooling. The Cadillac of VRF systems is actually the heat recovery system. In this particular case, what we do is we introduce basically a refrigerant switch. It is called a branch circuit controller, and it's sort of in the middle between the outdoor unit and the indoor units. And what this allows is for, back up here. What it allows for is simultaneous. For some reason, this is sort of showing up. The animation is not showing up exactly right. Here we go. So it allows for simultaneous heating and cooling. So you literally could have a conference room. I mean, nobody would really do this, but you could have a conference room in which you have a ceiling cassette on one side heating and a ceiling cassette on the opposite side cooling. It's not typical, but there are lots of cases where you actually need to have heating and cooling at the exact same time. Consider east and west exposure. Let's suppose that you have a building. There are certain times of the year where the sun is coming up on the east, and you might need some cooling on that east side. But on the west side, it's still a bit shady. So you might want to design a heat pump system because it'll actually absorb some of the heat in the refrigerant cycle and push some of the heat from the sun that's coming in from the east side and actually push it to the west side. But be careful, if you're going to use a heat pump system, you'll want to actually provide a system for the east exposure and a heat pump system for the western exposure. Placement of the branch circuit controller. Okay, so we've got this branch circuit controller. We need to find a place for this. For the people who work with architects, that's one of the first things that you actually want to talk about. Architects are not used to this device and where it actually belongs. So work with your architect and say, okay, we need to place this somewhere. It will make some noise. So I would recommend you don't put it, say, in above a bedroom ceiling. However, you could put it above a closet. You can put it in hallways, and it will be no problem. Indoor air quality. Oftentimes when we talk about VRF, we spend a lot of time with the variable refrigerant flow system, but we actually don't talk about the outside air requirements. So in virtually all VRF applications, one of the components is outside air. You need to bring fresh air into the building. So what we would recommend is you design a dedicated outside air system to, in essence, take care of all the fresh air that you need in the building. And we actually would recommend that you actually decouple them from the VRF system. So this DOAS, or dedicated outside air system, will handle the outside air load, while the VRF system will actually handle the internal loads like the people and the lights as well as the transmission loads that go through the walls and windows. Let's take a moment and do a little bit of comparing and contrasting of conventional systems and VRF systems. So the conventional system, it's typically made up of multiple components by multiple manufacturers. So, for example, you might have a chiller by a manufacturer, a cooling tower by another manufacturer, a boiler by another manufacturer, pumps, air handlers, VAV boxes, and such. You also have a network of piping and ductwork throughout the entire building. There are inherent inefficiencies when you have all these different pieces of equipment operating, and all of them obviously will take up space. So that is one of the things that one of the benefits with VRF is the fact that it's very compact, and the usable square footage that you actually take up with VRF system is far less than the traditional HVAC systems. On the other extreme, we have the self-contained units. So, as I got to this slide, I'm guessing that most of you have cringed because you know that when you see this system, you're preparing for a night of restless sleep as this T-TAC unit or self-contained unit cranks on and off, and the temperature, starts to vary wildly. Let's sort of take a look at how that looks, a conventional system versus a VRF system. Suppose that you're looking, you'd like to have a set point of like 72 degrees. The conventional system, what you will typically see is system turning on and then turning off, on and off, and on and off, on and off. With VRF, what you're going to see is the system turning on, but instead of turning on and off, will actually modulate. So what does this offer you as far as comfort? First of all, if you take a look at this black line, this dotted black line, you can have a wild variation of temperatures with the conventional system. This can be 4 or 5 degrees. With VRF, it's much tighter. This can be 1 to 2 degrees. So, hotels, and sometimes this is actually the driving factor for some of our hotel applications. The hotelier wants to provide a premium system and wants their guests to have good solid nights of rest. And so having these tight controls and also being ultra quiet, which we'll talk about in a little bit, is oftentimes the reason why hoteliers choose VRF for their systems. All right, so a myth. Sizing guidelines don't apply to VRF systems. Sometimes people will think, well, with VRF, since it's variable and it can speed up and slow down and speed up, slow down, I'm going to just grossly oversize this and put that system in. Well, that is not a good idea. We don't want you to undersize it. We don't want you to grossly oversize it. We want you to right size it. If you oversize systems, they're just going to cost the owner a lot of money. We can simulate, the performance of our equipment down to the room level. So there's actually no reason to grossly oversize your equipment. Another myth: VRF systems are only used in southern climates. We use VRF in Chicago all of the time, and we often use it as the sole source of heat. So we don't have backup heat. We don't have electric boilers. We can do systems here in Chicago where the VRF system provides 100% of the cooling as well as 100% of the heating. Our performance on our systems can range from negative 25 degrees Fahrenheit all the way to 115 degrees Fahrenheit. Cold climate designs and setups. So a lot of people will use ASHRAE 99.6 when they're putting together their designs. We would recommend, because of the the polar vortexes and the wild swings that we're actually seeing in temperatures these days, is that you subtract about 10 degrees from those ASHRAE designs. So, for example, in Columbus, Ohio, you might see the ASHRAE says to design to 0. Well, we would recommend that you design for -10. Of course, local codes prevail. One of the interesting things about VRF is how it is actually controlled. And I'll talk a little bit more about it in a moment. But one of the things to note is that the way our systems work is that last command wins. So if you have a building automation system, or if you're just going to use the built-in VRF controls, or the local thermostat on the wall, whatever the last command is what the system will do. This is particularly important in, say, school applications. So you might have a school where at 3:40, when all the kids leave and most of the teachers have left, and you're in the cooling season, you might say, okay, we would normally want set the systems at 72. We're going to do a night setback. We're going to allow the system to, say, ramp up to 80 degrees. If a teacher happens to be there at 5 o'clock and they set the temperature down because they saw that their thermostat said 80 and now they want 72 because they're going to be there for a couple of hours, the system will allow that. They can then reduce the temperature to 72 degrees and the system will run there. So be cognizant of last command wins. You'll want to do multiple sweeps with VRF. So in my example, what I would do is I would program a sweep at 4 p.m. to raise it to 80 degrees, and then I would program a second sweep at, say, 11 p.m. To make sure that everything is gone down to 80 degrees. And then, around 7:30 when people start coming in, then you bump it back up to 72 degrees. Incidentally, with our central controls, you can actually allow different bands for thermostats. So you can say, okay, this thermostat, which is located in this room, we're going to allow the user in that space, say, to operate between 68 and 73 degrees. So you can do that as well. All right, so let's talk about some of the benefits of VRF. One of the ones that are near and dear to me and near and dear to most owners is the financial impact. Money makes the world go round. So let's take a look at a 25-year life cycle cost analysis that I actually did for a hotel. What the hotelier wanted to do is they wanted to know, okay, I'm going to keep this hotel for 25 years. How much is this thing going to cost? This system going to cost me versus what I'm used to doing? I'm like, okay, we'll go VRF versus PTEC. Mr. Customer, does that sound right? Yes. So if we take a look at this 48,000 square foot hotel, the VRF system, the total life cycle cost was about $2.7 million. For PTEC, at that same 25 years, you can expect to spend $4.3 million. First cost, the VRF is definitely going to be more expensive. You're probably looking at right around $20 a square foot versus $15 a square foot for PTEC. Maintenance-wise, there's a big discrepancy, and also utility costs. So Let's take a look at it graphically. It can clarify the things a little bit. So we've got total life cycle cost. Red is the VRF system. Gray is the PTAC system. First cost, you can see there's a slight premium for VRF versus PTAC system, but there's a substantial maintenance cost savings as well as utility savings. So looking at the energy costs a little bit closer, a VRF system on this particular hotel would cost you about $20,000 a year versus the PTAC, which is going to be almost $40,000 a year. Here it is graphically. Okay, so moving along to the annual maintenance cost. I have a son who's 12 years old, and I often tease him. I tell him he's not all that bright. He really is, but I tell him he's not. But I could actually teach him to be the VRF maintenance man. In essence, with VRF systems, you change the filters, say, once a quarter, and you clean the condensing units with a garden hose or with a brush once a year. That's it. That's all you do with a VRF system. So there are huge savings when it comes to maintenance compared to other systems. One of the nice things about VRF is that it's all electric. So being all electric, it can fold in nicely with customers' strategic, electrification initiatives. It plays nice with, with solar, etc. From a sustainability perspective, if you design an HVAC system with VRF, you can earn a ton of lead points. So as much as 70% of your lead points can come from VRF if it's certified level, and you can earn up to 35 points if it's if you're seeking platinum level. One of the main benefits of VRF is creature comfort. Simply put, you can eliminate hot and cold spots. I've talked to a number of building owners and facility managers. Hot and cold calls are the #1 complaint by tenants. VRF eliminates that because you get heating where you want it in the quantities that you want it, and cooling where you want it and in the quantities that you want it. All right. Another myth. You can save money on using heat pumps in any application. That is actually false. If you have cases where you're going to need heating at the same time as cooling on a particular building, you really shouldn't use a heat pump system. You should use heat recovery. There is a premium to do that. So if you decide, hey, listen, we're going to try to do it, there are some strategies to try to apply it, but you, at the very minimum, you want to apply a heat pump, where you're going to have all heating and all cooling independent of each other. The other thing I like about the Mitsubishi's VRF system and our philosophies is the innovation that we do, that we have. It's constantly evolving, and one of the most recent evolutions is our 360 i3D sensors. In essence, what it is, it's an infrared sensor. It's an eye up in our ceiling cassette, and this thing spins around, and it detects heat signatures. And it can tell the difference between, say, a person and sunlight coming through a window. So in a conference room, for example, you might put this in there and then set it up such that if there's nobody in the conference room for 10 minutes, you're going to allow the temperature to creep up. even if the sunlight's actually shining through. Once it sees occupants in that room, now it's going to drop that temperature down to a preset condition, 72 degrees or whatever you actually have it set for. So innovation is one of the real key benefits of working with Mitsubishi in our VRF line. The controls is another reason. Anybody in the HVAC business understands that controls is a necessary evil, quite honestly. I mean, usually you have a multitude of manufacturers and pieces of equipment that you're all trying to speak the same language and work together. The great thing about VRF is that all those controls are actually baked into the hardware. So with controls, we actually daisy chain a 16 gauge 2-conductor wire from indoor unit to indoor unit to indoor unit to indoor unit back to the outdoor unit. Once that is done, we turn the system on, and the brains are in the outdoor unit. It will pull all of the indoor units, and you're ready to go. So it literally is plug and play. There's no special software, no special licenses. If you want to be able to control this, not from just this central control panel, which is basically like a small iPad, or actually it's about the size of an iPad hanging on the wall. You can run an Ethernet cable to this central controller, and you can control your system from a standard browser, Internet Explorer or Chrome, and there are no licenses, no special software. You can just control it directly from a standard PC. We also, obviously we can control things from a central location, but occupants they can adjust the thermostats as necessary. We can use third-party thermostats like Nest, or we can use our standard thermostats. It really doesn't really matter. All right, so I did speak about quiet operation, and not to get overly technical with dBA and sound levels. The easiest way to sort of describe sound is actually using this scale. So dBA, 20 dBA is roughly a recording studio. It's near silent. 80 dBA is a garbage disposal at 3 feet. So we're sort of working from the right to the left. The conventional air-cooled chiller is going to be roughly 80 dBA. The condensing unit at your house is roughly 65 dBA. Our commercial outdoor unit, 55 dBA. It's basically it's just a human conversation about the level of the human conversation. The indoor units, 32 dBA, and the ducted units are near silent. And in many cases, we've done actually projects in Chicago where it was actually a recording studio, and that was priority number one. The system had to be silent. Usable space. So a lot of times the driving factor is the owner wants to put a roof deck on the roof, or wants to recuperate usable square footage. VRF, in its by its nature and modularity, can be used to accomplish that goal. And I can't tell you how many projects that I've been involved with where it's a hotel who wants to put a rooftop bar on top of their facility, or amenities for apartment complexes. So recapturing usable square footage is definitely a positive for VRF. So as far as training, we do not like it when contractors buy our equipment and try to install it without training. So we have training facilities throughout the country. I think it's about 8 or 9 of them scattered throughout. And we offer a 3-day class, and it's not just a textbook. It's actually, we have laboratories with working equipment. So we do part of it classroom style, And then there's a lot of hands-on training that goes along with it. So day one might be the installation, how do you install the systems? Day two, we will talk about controls. And day three will be service and troubleshooting. So we highly recommend that contractors come to our training classes. For all the engineers out there, I highly recommend that you actually specify installing contractor must attend manufacturer's training class. So with that, that pretty much wraps up my portion of it. At this time, I'm going to hand it back over to Kevin, and he's going to cover some of the VRF case studies that we have. Kevin?
Awesome. Thank you, Vic. That was a really insightful and detailed look into VRF technology. I especially like the myths and facts that you shared in order to tell the full story of VRF systems, and I'm sure we're going to have lots of questions for you at the end of the presentation today. A quick reminder to those of you on the phone to submit your questions using the Q&A function within the presentation software. Now that we have an understanding of VRF technology at a high level and have peered deeper into how it works and is applied, let's look at a few real-life examples where applying VRF systems resulted in superior energy efficiency and performance for the building, some of the things that Vic talked about earlier today. The Uber Advanced Technology Group, located in Pittsburgh, Pennsylvania, is housed in a two-story, 110,000 square foot office building. The building mainly serves as a research and design facility for advanced technology at Uber, including self-driving automobiles. The building has a unique and challenging design in that employee offices sit side by side with car testing spaces. Those spaces produce high carbon dioxide levels, as you probably can imagine, making ventilation inside the building a critical component of the overall HVAC system design. In addition, Uber's environmentally conscious culture places a focus on energy efficiency. So when Uber went looking for an HVAC system for their building, ventilation management and energy efficiency were at the core of their search. The company worked with a local distributor, Comfort Supply, to select a variable refrigerant flow HVAC system along with premises dedicated outside air systems and diamond control solutions. According to Justin Kern, Senior Commercial Sales Engineer at Comfort Supply, quote, VRF was chosen for the quietness of the system. In addition, the control solutions package entailed a full graphical interface for the building. We tied in the VRF systems, DOAS system, electric heaters, and exhaust fans. According to Aaron Doubt, Facilities and Special Projects Director at Uber ATG, quote, having the ability to control each room with its own set point or even a small section of rooms with VRF has been great. It really makes it easy to not have those big temperature deviations or fluctuations that you would have with a traditional system. Not to mention the ease of having branch controller boxes in each zone that tie into the BMS. That has really helped us in our day-to-day operations. The end result on this project was an integrated VRF, DOAS, and controls solution for Uber's management team, and a comfortable space for the employees to continue their important research and development activities. Since 1984, the Bicycle Casino, located in Anaheim, California, has been a gaming destination in Los Angeles. With the addition of a new 118,000 square foot, 7-story, 100-room hotel in 2015, the Bicycle Hotel and Casino is now a high-end boutique resort destination. In addition to the hotel, the building also includes a full spa, restaurant, bar, offices, fitness areas, meeting spaces, and more. When designing the hotel, the engineer and architect were looking for a high-performance, unobtrusive HVAC solution to provide personalized comfort and whisper-quiet operation in guest rooms and across a variety of spaces. They turned to a variable refrigerant flow system to satisfy those needs. The selection of a VRF system came with many other benefits aside from the quiet operation and personal comfort control the hotel desired. The hotel was also able to achieve an installation cost savings of $350 per indoor unit installed, which amounts to $64,000 in savings across the 183 units installed in the hotel. In addition, the installation was completed in just 50 days, which far outpaced their goal of 10 to 12 months. The use of ductless ceiling cassette indoor units also enabled the hotel's owner to make guest room entryways 3 to 4 inches taller, which translated to an overall bigger feel in the guest rooms. This, along with a quiet operation, ultimately leads to a better experience for the hotel's guests and contributed to the high-end nature of the hotel. The end result was a win-win for the Bicycle Hotel, reducing their overall installation and energy costs while introducing a better experience for their guests. Corey Hampton, an estimator with Thermocool, the contractor who worked on the project, said, quote, "In hotels, you can really hear the air conditioning. With conventional HVAC systems, you just can't sleep. But Mitsubishi Electric is super quiet. You can't hear it. For a hotel, that's a real advantage." The last project we'll look at today is the AC Marriott Bridge Park Hotel, built in 2017 and located in Dublin, Ohio. The AC Marriott is a 104,000 square foot, 8-story building. Dublin, an affluent suburb of Columbus, Ohio, is home to several Fortune 500 companies and hosts the renowned Jack Nicklaus Memorial Golf Tournament each year. With a resident population of 40,000, peaking to 80,000 during the daytime, luxury hospitality was needed to serve those commuting in for both business and recreation. The hotel was originally designed around a water source heat pump system based on its efficiency and individual room control. The developer brought METUS into the project to look at VRF water source systems just before the bid was about to go out. The developer liked the technology, especially the equipment and installation savings of over $500,000 versus the originally specified water source heat pump systems. Water source VRF also improved the guest experience at the hotel. By eliminating a compressor-bearing unit within each individual hotel room, guests can sleep in a more quiet and comfortable environment, which is especially important to Hotel General Manager Orkan Turkay. He said, quote, "The most important thing for our hotel guests is that the HVAC operation is simple, comfortable, and unnoticed." In addition, the hotel was able to tie the water source systems into a building management system. The controls enable the hotel to remotely manage, diagnose, and troubleshoot any problems that occur with the system. According to the AC Marriott's chief engineer, these controls give us the advantage to make a guest stay a little more flawless. From a maintenance standpoint, Diamond Controls has made it easy compared to other properties I've been at. Having that central control system, I can just jump in a room from the interface, and 75% of the time, I can fix the issue right there in the program. This is much more convenient rather than having to bug the guest, go to their room, and start pulling the equipment apart. In the end, Water Source VRF and Diamond Controls were a win for the AC Marriott Hotel and helped improve the guest experience. There are a number of takeaways we'd like to leave you with at the end of today's presentation. Those takeaways include, number one, VRF is a mature technology and the preferred method of heating and cooling in many parts of the world. Number two, contractors who have installed one-to-one split systems can learn to install VRF systems with manufacturer training, as Vic talked about earlier today. Number three, VRF systems are less complicated for engineers to design and provide for operation in outdoor temperatures from minus 25 degrees Fahrenheit all the way up to 115 degrees Fahrenheit, and in some cases a bit beyond. And VRF systems reduce first costs and lifecycle costs through energy efficiency and smart design. The HVAC industry is ever evolving, and we believe firmly that it will continue to do so well into the future. METUS will continue to invest in developing new technologies that further advance the energy efficiency, design freedom, and installation flexibility of HVAC systems to meet and exceed the needs of the market. That concludes the prepared portion of today's presentation. On behalf of Vic Chale and the entire Mitsubishi Electric Trane HVAC US organization, I want to say thank you for the time that you've chosen to invest in today's webinar. We both hope you were able to gain new knowledge and ways to get started with VRF systems. On the screen, you will find a number of resources available for your use after the presentation. These resources include our website, metahvac.com, a link to subscribe to industry-specific quarterly newsletters, and links to the case studies we discussed today, along with a library of over 200 additional projects that can help you in your sales and specification efforts with VRF technology. With that, I'll now turn the floor over to Herb to close out the presentation and open it up for questions. Herb?
Kevin, a big thank you from us over here at Engineered Systems. Thank you to Victor as well. The presentation was fantastic. And now, as you said, we'll have you guys address some questions that have been submitted throughout the program. First question, when you're comparing VRF and chilled water, when do you choose between them?
That's a great question. You know, both are technologies that we commonly see here in the U.S. I think really, and Vic, I'm interested in your thoughts, especially in a northern climate. It really comes down to the application and the goals of the building owner. Would you agree, Vic?
Absolutely. Here in Chicago, what we often see is chilled water systems and boiler systems in office applications. We like to use the VRF systems where there are lots of little zones. That's where we really shine, is when we have lots of little zones. If you, our biggest markets here are probably hotels, apartments, dormitories, and senior living centers. Those applications typically are not good candidates for chilled water systems, just simply from the size. So hopefully that gives you a good idea as to when to choose, say, a VRF system versus a chilled water system.
Okay, great. Moving on to the next one here. How critical are zone heating and cooling load calculations when sizing VRF systems to ensure proper heating and cooling of the zones within a building?
I think that's a critical component. I'll say a few words, and then Vic, from your perspective, when you're working with engineers, I think it'd be good to talk about that from a design standpoint. But obviously, sure, you want to talk about when you're designing the building, you want to look at how the space is going to be used. One of the hallmarks of VRF technology is that while they're very important from a design perspective to calculate in zone loads and overall load of the building, the flexibility of the technology and the ability to change it and adapt it with the needs of the building is a critical component of VRF itself, and that you can go back and redo those calculations in the future should the needs of a space change. So Vic, when you're working with an engineer, when you're designing call it an office building, for example, and you're looking at loads within each zone, how do you have that conversation? What goes into that?
Well, that's a great question. So that's generally where we start when an engineer is looking to lay out a system. Question number one is, what are your loads? What are your heating loads? What are your cooling loads? In the northern climates, most of the time we're dictated by actually the heating loads, simply because if we can provide enough heat for the system, the cooling is no problem. So question number one when working with engineers is, what are your loads? Question number two are, what style of indoor units do you want? Question number three is, how do we want to zone everything?
Okay, moving on to the next one. What are some of the best practices when installing a condensate line from a wall-mounted evaporator unit?
That's a good question. Condensate removal obviously is an important part of HVAC in general. You probably, Vic, probably don't want to hide everything in a space you can't get it, correct?
Well, sometimes. So the wall-mounted unit, there's a couple of ways to actually do it. So you can use a pump if you'd like, a condensate pump. You can also just use a drain line and have a drain riser. Say that you have a five-story building, you might run a condensate riser from the top to the bottom, and then out some kind of floor drain or whatever. It's actually, if you can use a gravity drain and avoid using a condensate pump, That's the preferred method, because that's one less device that can have an issue. If you have to use a condensate pump, you have to use a condensate pump. If you're using a condensate pump, our units actually have a sensor so that if the condensate happens to build up for whatever reason, maybe it's a failure in the pump or maybe it's a blockage in the line, the unit actually will turn off. But the best way to do it is to use a condensate riser.
Great. Next question here. If your building needs a DOAS that requires ductwork, does that offset the benefit of a VRF system not needing ductwork?
I wouldn't say it offsets it. You know, the DOAS and ventilation in general, as an aside, are becoming a much more common part of HVAC system design around the country and around the world. We're seeing an increased demand for flexibility in ventilation solutions to be applied. The good thing about DOAS is that it can work two ways. You can couple it with a HVAC or VRF system, or you can completely decouple it. Vic, when you're talking about building design, I'm assuming you probably see a hybrid of both.
Yeah, definitely. We see a hybrid of both. But I will tell you, I mean, the question being, does it offset it? It offsets it a little bit, but in contrast, if we were to take like the conventional system, your ductwork is going to be size X. With VRF, with DOAS, the ductwork will be 25% of X. So there, even though yes, you'll have that component, it's much, much smaller.
Great. Next question here. Is there ever a time when VRF is not suitable for a building? Are there minimum and maximum square foot requirements that VRF has to have to be applicable?
I would probably say there's, in my opinion, I'll give two examples first, and then Vic, I'll let you chime in with yours as well. You know, I think minimum size is probably something you want to keep an eye on. You wouldn't put a VRF system in a 2,000 square foot house, for example. That's completely overkill for the application. That's kind of number one. And on the maximum side, you know, there's flexible ways to design a system, especially with water source VRF, that can enable you to install VRF in 40, 50, 60-story buildings. The second one, call it restriction, if you will, is rooms that require or service or applications that require a lot of air changes. So think operating rooms, clean rooms. Those are probably not the best application for a VRF indoor unit, just due to the fact that you can't get enough CFM through it on a regular basis. Vic, do you have any other watch-outs, if you will, when it comes to VRF?
Yeah, just in general, VRF is a zoning product, so we do really well where you have smaller zones. So I'm going to say somewhere between 400 square feet and say 1,600 square feet. That's the typical application. That you'll have an indoor unit per 1,600 square foot or less. The other place that I wouldn't recommend using it is in big box stores. I mean, VRF for a Best Buy or a Home Depot or these large warehouses isn't going to. It'll work fine. It'll work great, but it's overkill. It's just it'll cost too much to do that. There are other systems that'll be less costly to heat and cool great big spaces like that.
Okay, guys, this next one's a little long, so bear with me here. In areas where there's considerable solar gain, yet the outside air is cool, can you coordinate the DOAS with the VRF to take advantage of the cooler, free, low humidity outside air and not use as much energy to run the VRF?
That's a great question. I think it probably lies in the style of DOAS you use. Vic, would you agree?
I would agree with that, and so the answer, yeah, for sure. If you can provide the cooling with cool outside air, that DOAS system is going to be set up to bring a certain amount of air into the building. And if it doesn't have to work very hard to do it, it makes a whole lot of sense to try to cool, say, the building with DOAS and then trim it out with the VRF system.
Okay, guys, we've got time for a couple more here. Can VRF systems benefit from free cooling economizers in the shoulder months, say like traditional air systems can?
We don't typically, or at least I don't, typically see economizers installed on VRF systems. I don't think that the need is really there. Is that your understanding as well, Vic?
Yes, we see that, I don't know, how do I best explain this? Sort of the same way that I answered the last question. If we can bring in, say, 55-degree air in the shoulder months using DOAS, we'll do that. We'll bring in 55-degree air because it's, in essence, it's cooled for free. And then allow the VRF system, to trim it out, whether it's a little bit of heat or a little bit of cooling. So it's not that uncommon.
All right, let's talk PTACs versus VRFs, specifically for hotels. Can you touch on a few of the advantages in that application? And also the comparison that you had up there, does that include labor?
Vic, I'll toss this one to you since you had those slides in the presentation. Okay,
sure. Yes. So the easy answer for the last part of it is yes, the numbers included labor and installation. The features and benefits, VRF is going to modulate, so you're going to have much tighter temperature controls. It's going to cost the owner a whole lot less money for maintenance and utility costs. The downside is that you can expect, say, $5 a square foot increase over PTACs on first cost. So for hoteliers that are going to hold on to their properties for a number of years, it makes a whole lot of sense.
Hey guys, looks like we have time for about one more question. Can you comment, well, going back, Vic, since you were big on myths, can you comment on the myth that space temperature setbacks should not be used with VRF systems?
Go ahead, Vic, take this one.
Well, okay, so space temperature setbacks should be used with VRF systems. However, you don't want to overuse them. So, for example, you may not want to allow your building, let's say your temperature set point is, say, 72, and that's the typical what people like in their buildings. You're not going to want to set that back, night setback to, say, 55 degrees, because will be just too cold. The thermal mass of the building, with a thermal mass, it'll actually just take too long for the VRF system to catch back up, say, in the middle of the winter. So, yes, you should have thermal setbacks. Let's say it's 6 to 8 degrees setbacks, which is fine. You'll save a lot of energy, and then you start up your system in the morning, early morning warm up, and then you just let the VRF system just run. So you should use setbacks because it saves a lot of money when people are not in the building.
And you know what, guys? I lied. Looks like we've got time for one more question to beat the buzzer here. On a heat recovery system, how many refrigerant lines go from the branch circuit controller to each indoor unit?
There's 3 lines, correct, Vic?
Actually, so from the branch controller to a sub-branch controller, so there would be 3 lines. But from branch controller to any indoor unit, there will be 2 lines. Typically, those 2 lines, you'll have, say, 3/8 inch line and a 1/4 inch line. So those 2 lines will be, generally speaking, there's going to be line sets.
All right, gentlemen, that's all the time we have for questions today. Everyone, please join me in thanking Kevin Miskowitz and Victor Chale for their presentation, as well as our sponsor, Mitsubishi Electric Trane HVAC US. If you have any additional questions or comments, please don't hesitate to click the Email Us button on the console. As you exit today's webinar, please take a couple of minutes to complete our survey. We strongly welcome your detailed comments. Also, please visit www.esmagazine.com/webinars for the archive of this presentation, as well as information about our upcoming events. We appreciate your time and hope you have found this webinar to be a valuable experience. Enjoy the remainder of your day.